so I can flip my screen, or so I could flip my Microsoft Surface around. Because if I leave this on, the camera should, like, with the orientation of, because I'm using a Surface Book, so I could take the screen off and then flip it around. It comes down and lays flat, but the camera now goes right up my nose, so you don't want to see that. Well, if you do, that's weird. So I share my screen, and we get this weird thing that goes on in here. Whee! Isn't that great? All right, so flipping the screen, detach. You're flying through space. And boom. No, do not turn into a tablet. So, here you go. I guess it was chapter 16 and chapter 8. And I have this broken down, this exam review, into 2 parts. These were the practice problems that Dr. Ghosh would assign based on these chapters, right? When previously, before I started teaching it, they didn't give homework. I guess there was so much rampant cheating, or that's the way they felt, that they would give quizzes. So in preparation for the quizzes and the exams, these are the problems out of the book they suggested that people do. So I have a separate video that I did from not last fall, but from last spring, that I have posted up and I can share, that where I walk through. It's in 2 parts. Part of it is, I believe, I walk through these problems, and then part of it is a recording of a limited amount of exam review, like live. So I don't necessarily need to go through all of these things right here, but this walks through some basic break problems, the ones that are in the out of the book, and these are the solution manual answers. Let me hide that thing as we're walking through there. And here's an external break. I didn't ask any of those for the homework. So generally, if I didn't ask it in a homework, I won't ask it in an exam. Although it is kind of fair game, just to make that clear. And if you look at the way the course used to be taught, right? The homework is just to try to get you to work on this, but this other material is kind of telling you that you should learn how to do that, learn how to do all the problems, but I think I wouldn't ask that. There's a band break problem. Those are pretty straightforward. I think the really important thing in these that I see missing that students don't do are the free body diagram is a real key important thing. We want to make sure we get that free body diagram to be able to make the connection between P1 and P2, or, well, in this case it's because the pin is right here, so we actually are making a connection between the force, actuating force, in P2 right here. Something that many of my students mixed up was the recognition of which one is P1 and which one is P2 in any of these. And because this one right here is going clockwise, this one is going to be P1. And were it to go counterclockwise, this one would be P1. Hopefully that's something that's clear. We had some power screw problems. Most of those have to do. We have some type of thing that has to deal with torque. And you can see that there's this problem's interesting because it has a horsepower that's required to be able to lift. I believe this is a power screw, and it's got. Well, I guess it just has to move a load. It isn't saying necessarily it's got to lift it. It's a good problem to work over. Here's another one right here, and I think it's yes, it's another torque problem. This one has a collar in it, so it not only does it have the friction torque right there because of the threads, but also we have to address the collar as part of that. And here is a problem where we have so this is a bolted joint, a preloaded bolted joint, as I try to refer to it. And I think this is, yeah, this still is the solution manual, although they did nice pretty colors right there, right? So anyway, some of the difficulty can be in if you were asked to find K, and the difficulty in asking that type of problem on an exam is that can take some time. But let me end the show. I'll discard the stuff I've written there. It's important to go back to the books, right? And secret copy of Shigley. Again, I don't think it's that secret. All you have to do is Google it. But if you go to the bolts section in here, and we go down to the joints and get those frustums. I always pronounce them wrong. You have a bunch of different equations, and that could be frustrating for any student. And it's a little frustrating for instructors. But so the frustum here is like the basic equation, and sometimes I use this one. Let me see, I can write on this, can I? Comments, close that stupid thing. It'll let me write now. All right, so this equation right here, and you guys can see this, right? There's somebody out there. Anybody? Speak up and say hi. Nothing. Maybe you're chatting with me. Okay, okay, cool. I'm sorry. It's just it just gets very disconcerting. I'm trying to somehow figure out some way to be more interactive during these sessions. It's not to sing the blues, but I'm getting kind of frustrated by that, to tell you the truth. I'm a teacher, man. I'm not just somebody that talks to a computer screen. Anyway, so anyway, the frustrating thing can be there's a bunch of different equations here, but that's like the frustration maybe in engineering sometimes, that we want to, there is sort of this natural desire to want to find an equation, and one of the most important things is that we use the equations correctly when we do find the ones that seem to be applicable. This is just the version where they've made that alpha into 30 degrees. And if you read this one carefully right here, this next one, if they have two identical springs, now instead of finding the individual frustums, right? Because like sometimes you might have a, let me take that back. Will it let me erase? No, it makes the eraser turns into a thing. Let's see, and there's not an undo button. That's the default up here, is there? Yeah, screw it. Yeah, so I'll draw this one is because I already made them kind of look pretty much that's interesting how that looks. Bing, 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 bing. Anyway, this one is the case right here where this is the total km, whereas made all of the things that color. Let's see, if you had the case right here, I'll exaggerate it. And I think what I have to do is like a done right here. I guess I'm stuck with the same color. So if we had, in this case, we're going to have 3 frustrums, right? Like 1. That was supposed to be a 1. Like you can't, it won't let me draw. That was supposed to be a really small number. There you go. 1, 2, and 3. That was supposed to be a 3. right there. Then we have to find to find the Km. We take 1 over 1 over. You gotta draw slowly. That's the key. Oh, that was too fast. You get the idea, right? 1 over K1 plus 1 over K2. Let's don't do that. 2. That's supposed to be 2. 1 over K3. All right, whatever. But if we have this case right here, we can simplify it by just writing one equation. And then they go ahead and they say, well, then they sort of skip one. They could have just put that 30 into that alpha, but instead they say, well, not only that theta is, the alpha is 30. We also know that dW is often going to be dW being the width of the head or the nut, right? And that's the thing that decides what capital D is going to be, right? And they also said, well, that the capital D out of the frustums is the same thing as dW. Actually, they're saying the diameter of the washer, I should say. That's so. What you have to assume then is there is a washer involved, right? And it's the washer that's making the decision of where that frustum starts. But if you use those two things together, you're able to reduce it into one equation. So and then let's see. And then they start to talk about the fact that you can you can reduce this to a simplified expression and then make a comparison to previously done work where people tried to find this dimensionless ratio and this aspect ratio between the diameter and I think the length of the joint. So anyway. The point being, the reason why I brought this up is that, let's see, we go back to right here. When we're solving a problem or we're reading through the solutions to problems, it could seem like I don't know which equation to use in which case. I generally have stuck with this equation right here, right? Because it's probably the most generalized, except the fact that they decided to use 30 degrees, but we're not given any other guidance except that 30 degrees. So a lot of times that's the equation that I will go with. But you can see back in here, yes, they went with K1. And they're showing you using that equation that I'm referring to find what K1 is. Then they're doing a little bit of geometry to figure out what the D's are going to be. And that's, in this case, this is. So I believe based on this, if I'm reading this correctly, they used this for D, for the D of big D1. Where's the thickness should be 1.5. So I'm trying to decide which one they made. Oh, okay, the top frustrum is T was 1.5. So there's your T, yeah. And then they did the lower one. Yes, that's okay. No, this is 1, and this is 2. But they had to do some geometry at some point to be able to figure out. Yeah, right here. To figure out what this dimension is so that they could do 2. And that's often a frustrating, no pun intended, part of this. And then lastly, they did 3 here they did a cast iron one. So you could not use those other equations. You had to use the one that I said that is usually my go-to equation. One of the reasons you couldn't use it is that these two flanges were not the same thickness. Another reason you couldn't use it is because they had a different elastic modulus, which I'm not seeing inside here. Oh, no, there it is right there. There's the elastic modulus. They didn't bother calculating it right here. And then they get the Km. And then the most important part of most of these problems, this one they were just looking to find the member stiffness. But quite often the most important part, I think, is to find that C, right? So this is the continuation of that problem. But now, or maybe no, they just made a difference. This is actually the same problem. They just made it aluminum. They put an aluminum plate on top of it. So that's a little bit more work. And then now we actually have the implementation of these, right? Where we're going to find that all-important C. And we'll often find that C is 0.2, or right around that range. So if you get something crazy that isn't 0.2, chances are you did something wrong. These happen to be the problems that I did in class for this particular this example. But anyway, I'm talking through these problems, but let me go through and do some of the practice problems that I have for, let's see, and you guys, I think, use a different method here. This is also an example that I did in class. You guys use a little bit of a different method, I believe, in Dr. Orlup's class for those offset problems. All right, so what would you like to do? Would you like to do a shoe brake problem, a band brake problem, a power screw problem? I have something here called bolt nomenclature. This is from a previous professor at Coast Guard. I was like doing like an assistant teacher kind of thing that semester with her. And then they gave me like one student the next semester who needed to redo that she had failed. And then it was my class for the next 3 years. So you see F12, that's what it was, her exams. Yeah, so this is me. This is one that I did right here. And I usually put this stuff in here because I do it up on the board. So let me stick in some blank slides to walk through these instead of just showing you the results, because I posted these things. So let me end this show, discard, and stick in. Well, first off, let me see if you guys have any chats in there to tell me what you would like to see. What would you like to work on? What kind of problem? Anyone? I got 5 people here, right? Let's see, Brad, Jack, Mernon, and Renard. Or Ray, right? Ray. Sorry, Ray. Anybody? Chat? You still there? Power screw? Power screw. Let's do a power screw. Okay, so let me see. I'll come back up here. And whereabouts are you? First off, let's move this guy here. I think I could probably do this in one. Okay. So for this power screw here, I didn't bother writing out the solution, did I? Nice. Well, I have, I think I did it on the next page. Yeah. So a single-threaded power screw with square threads is used to lift a 10 kilonewton load. The major diameter of the screw is 40 millimeters, and it has a pitch of 6 millimeters. There is no collar, and the thread coefficient I would think they would mean the coefficient of friction, 0.09. We want to find the torque to raise the load. What is the overall efficiency of the power screw? So I get my book out, and I will keep that this time, and I take a look at my power screw section, and I find here's my thread dimensions. So do I need those yet? That's probably one of the first things I want to do is take a look at the thread dimensions. Yeah, okay. So here you go. This is, we want to take a look at the power screw thread dimensions. And we can see that the threads are going to be, if we're going to have, I guess it didn't show this, but a mean diameter is going to be this right here. Yeah. We call this DM. And that turns out to be DM is equal to D minus 1P, right? Because it's P over 2, or is it minus P over 2? Let me, 1 second. Yeah, I think it's minus P over 2. Don't hold me to that. I think it's P over 2. Let me double check. Yes. P over 2.
Yeah.
And okay, so in doing this, we have a couple. We once again have a couple equations that we could choose from. It's really going to be. It's going to. This they asked for the. We want to raise this load, so we're going to use this equation 8.1, and there is no collar. So we want to be careful when there is no, if there is a collar, that we don't just, if they ask for the torque to raise, that we don't just use this equation. We also have to add in what the collar is. But they don't show that equation. But if you were to go into the, here, into the example right here, you would see that that would be the total equation that we would use for this thing. But we can come back in here and we could paste that. So that's the main equation that we want to use right here. So we want to find all the things, but we don't, in this case, we don't need that collar because there is not one. So all we do here is to find the torque to raise, and the force that we have, the load, is going to be, let's keep it as kilonewtons, why not? What we can do is we could use millimeters, right, along with this. Okay, and I never did calculate what dm was, but dm was equal to d minus p over 2. And we were told that that was 40 millimeters minus 6 divided by 2, right? I almost can do this myself. I think it's 37. I think that's true. And since it's kilonewtons times millimeters, the kilo kills the milli. And we get the right here. And the lead, that's a little confusing sometimes. The lead is equal to, let's say, n times p, where n is whether it's single or double or triple, whatever. Well, most of the time we deal with single threads. Did Dr. Orlip ever mention a very common triple thread? Do you know of? Are you guys familiar with the triple thread? You probably see one every day. Maybe several times a day. I'll keep this because I want to see if you guys know about the triple thread. We are here, right? Not sure. Well, I actually have one right here in front of me, and I can show it to you, so you know what I'm talking about. Let's see what's mad at me. Camera right here, boom. Now you get to see. See, is it going to open up the camera correctly? Yeah, there you go. By the way, that's a mural on my ceiling here in my guitar room. Right here, here you go. There's a triple thread for you. They say, well, how do you know that's a triple thread? Well, look at the beginning. Let's see if you can see inside the cap. But you could see one in real life a lot easier than this. Nope. Because they made, the Poland Springs makes these environmentally friendly. They make the caps really small. So another place that you'll see it is on your toothpaste tube, on your toothpaste cap. And what you want to look for is you look for the beginning, like the beginning of each thread. You could see that there's actually 3 beginnings of each thread. That means that this actually is a triple thread. There's actually, you can think of them as 3 threads in parallel with each other. And I wrapped some wire like just around the bolt to kind of give you the idea of how that works, right? That there's 3 parallel threads going at the same time. And if you have a lead, the lead will be like from the black thread to the black thread, right? So there'll be 3 threads, but the pitch is just each one of those wires, right? But so I just think that's kind of an interesting thing that we're always seeing triple threads. I tried to print one out, but it never worked. So the threads I couldn't get the threads engaged. I printed them out a couple times, but I'm getting angry at my 3D printer. So anyway, in this case, we had a single thread, right? So that means that L is equal to P. So we could just put the pitch in there, and I think that this right here everything will cancel, will be unitless, right? Because we're getting torque, so we could see that F times D, that's enough for our units and our torque. So the rest of our things we just keep it as is. We don't need to necessarily turn them into meters like I usually do. So we get the coefficient of friction 0.09 and the mean diameter 37, and divide by pi and multiply by 37 and subtract out 0.09, but also make times the pitch. Well, that was also called the lead right here. And if we do that, I could do it by hand right here, but I'm extremely lazy, and I've written the same thing over here. That's 26.32. And that's in Newton meter, right? Because the killa killed the milla. And then if we want the overall efficiency of this, come back into the book, and we can see that the efficiency is going to be related to the idea of the efficiency is that the friction is causing us some losses. So what would be the equation? What would be the raising equation if you were to have 0 right here? If you were to take, how come you're not doing that for me? Oh, you are. It's just slow down. If all the F's went away right here, what you would end up having is the torque O right there. I don't know, maybe this torque 0, maybe 0 friction. So that would be the torque that would require. You would still take some torque to lift the thing. It would be really smooth. So the efficiency is just the ratio of these two things. And I don't think there's any benefit to actually calculating that right there. So, or this second part of there is not really any usefulness to that, I think. So we'll just grab that. And I wonder if my screen grab will Yep, it did. It put in those little red things. Okay. So coming back here, we say that TO is going to be equal to, once again, we have the kilo and the milli, so we have 10 kilonewtons, and the lead is going to be equal to the pitch, so that's going to be 6, right? Yep, and 2 pi, and if you were to do that, cheaters. Oh, I didn't do it right here. All right, so we go 10. It's an interesting number to get something in between, I think. You could kind of like just visually determine what the extent of the friction is going to be. I think we get 9.549 Newton meters. So if we have the efficiency is going to be TO over TR, or 9.549 divided by 26.32. 26.32, boom. Sure enough, we get 0.3628, which is our answer. Not a tremendously difficult problem. I have asked before, one of my very favorite problems, and I don't know if I'm giving away, I haven't written the exam, but one of my very favorite problems that I've written before, and I probably will use again at some point, is I did this. And, sometimes I think it would be an interesting thing to just give to, in the review session, give out the problems, or not tell anybody that I was doing that, but work through the problems that are actually going to be on the exam. It'd be kind of evil thing to do. And then all the people that attended the problem would be attended the session would be the ones that would benefit from that. So what I did here is I put in and I gave in some torque, right? Or a torque would be on this shaft right here. It's a very weak shaft, and we have some kind of weight up above, and maybe there's a collar right in here, so that this is the place where there's going to be some friction in there, and we have a threaded piece like right here, and maybe there's some bearing or something right here, right? So this right here is a housing. So there's threads right along here, and there's like a threaded nut inside the gear, right? So I want to know if I have like no, that's not true. Okay, so I say that let's see. Okay, so I say what this dimension is. Like I say, let's say that's a really small. It's a 1/2 inch diameter, right? And I give you what the steel is of this, right? So that you can look up the yield strength. And I ask you, what is the capacity? How much weight can I lift if I have this shaft and I need to have a safety factor that has to be greater than 2, right? And a static one, right? So based on yield. So what you would have to do here is, well, first off, you turn it into the yield strength into into shear yield, right? Then I go backwards, and the only thing I know about this is the torque. So I go the tau max is going to be equal to that shear yield divided by that safety factor that I had, and I know that's going to be equal to TR over J, and I have that from the 1/2 inch right there, so I'm able to find a torque. Now I have a torque, I have a maximum torque that this shaft can handle, and now I have the torque. That's the torque to raise the thing, right? But now I have this F dm over 2 times a bunch of goggly gook plus this f times I think it's dc fc over 2, right? So now I can pull out what my f is, and that's the answer, right? This is the f max is going to be equal to that's what my weight is going to be. Isn't that an interesting problem? Oh, by the way, one of the things you have to do. Is there like a gear rate? Yeah, yes, yeah, no, absolutely. I'm sorry. I totally wanted to. Yeah, yes. So you have to like. This would be like. What do you say? I got to go what the gear ratio is right here, right? So the gear right here is going to have larger right here. So this would be like D1 and D2. And I'm going to get this backwards if I'm doing this live right here, right? So we have the T max. We have to make the, no, it can be a larger maximum. It could be a larger torque, right? So, yes, D2 over D1. Yeah, you're absolutely right. So that's the raising torque. Isn't that interesting? I like that kind of problem. I wish I was more creative and then I could come up with more problems like that, where you had to use ME470, you had to use something else that you knew from here, and then you had to go through the thought process, the engineering thought process, and like this causes this, causes this, causes this, and then you get to a desired outcome, and it's also a practical problem because it's something that you would actually want to learn how to do, right? Because there's maybe some kind of part in here that's going to stop you from going to be the limiting condition. So anyway, I figured this problem is so simple right here that I figured I wanted to add something to power screws, and it's the only power screw I think I have in the practice problems. So let's take a look and see anybody else have any requests here. Snooze you lose, haha. I don't know the context of that. Anyone? Bueller? What time we got? 12:30? Anyone? No? I could just talk to myself. There are other people here, right? I don't think I should be sharing this video when after I'm done recording it. Oh, yeah, bolted cantilever joint. Okay. Yeah, so I wish I had like some more complicated bolted cantilever joints. It looks like that I only have listed here this one, and it's a little simple, I think. I meant to make more complicated ones. Is there any others? That's weird. It seems strange to me that I didn't make more of these, so my memory isn't all that great, but I seem to recall I've uploaded some others. Let me double check. Did I upload any onto Blackboard? My Blackboard 470 exam prep.
Dr. Deal, I have to head out, but thank you for doing this. I appreciate it.
You're welcome. Sorry I wasn't there when I was supposed to be there, or I said I was going to be there, but it was a misunderstanding. So you got to practice. Yeah, so have a great weekend, right? Let's see, practice for exam 2. And do I have other problems? Yeah, so I had to make some more. I had to make some more problems. Yeah, so there's only that one problem. But let's go over it. Let's go over it as if informally, because I think one of the bad parts about this particular problem, or about the one that I chose, is that it's a bit too obvious how to approach the thing. So maybe I will discuss that a little bit further after I'm done working through this. So I see. I have one that's. I think I had some old ones. That's what it was, that weren't very good. And I decided to get rid of them. And I don't know why. Maybe I wanted to use them for something else. I wrote at the top of one of mine, foobar, which you can look up what foobar means. Okay, here we go. Well, the main thing we want to do here is, if this was the problem that was going to be asked, is to first figure out all the unknown things, or the things that we had to gather from the book. Okay, so this is a 1/4 inch, by 1 inch long, 1 inch wide, I guess. Yes. Not long. So this is the thickness, right? So this is the plate is 1/4 inch thick, and it's made out of AISI 1018 cold drawn steel bar. So that might be one of the things that we want to look up first, is to find the yield strength of that bar, right? And it doesn't say anything about this guy back here. Sometimes we might want to know, like, we might also want to do some analysis of here, but they show it's like really thick, so it's probably going to be okay. So I'll write this SYM for the member, and if we were to look that up, let's see. Did we not do that? Yeah, I didn't do that as part of this problem because I wasn't asked for it. That's why. When the find here was to draw and label the tau and the tau prime and the primary and secondary stress vectors on each bolt on the figure to the right, and then find the safety factor of the worst bolt. Okay, so it wasn't actually asking for the stuff in the member, but that might be something that we could have been asked. So let's instead go to the bar is secured to the support with 2 1/4 inch 20 thread per inch UNC grade 1 bolts, and we've already provided that they're 36 KSI as their yield strength. The bolt shank, not the threads, is in the shear plane. We could also have used shoulder bolts for that. So that first part here, they just want us to sketch in the primary and secondary. So you don't actually even have to calculate anything. We could just write in, and usually I've been using forces. I guess maybe I think I was following somebody else's suit here, but they could just as easily be shears right here. So there's the primary, right, is going to be right here in that direction, and the secondary, because this force right here causes a moment that goes about there, we are showing, here's the tau double prime, and here's the tau double prime over here. That right there, it represents the moment that's being applied because of this force. I have to remember that in this case, this is we don't draw free body diagrams necessarily for this. What we're drawing is the equivalent forces due to this force and its location. So that tau prime is going to be 1/2 of this force, because it's divided by 2 bolts, and divided by the bolt shear area. And in my so if I want to find the magnitudes of those forces, I go F. I could color code this in Christmas colors. We have F prime is going to be 150 divided by 2, or 75 pounds. And then we could say F double prime. Now, if this was going to be much more complicated, we could actually figure this out on our own. But probably better for us is to go through the process. I'm not sure Dr. Orleb does this exactly the same way as the book. But if we go to the book and we go to let's see here, which one is it going to be? Fatigue, bolted, riveted joints, loaded and shear. Yeah, so we could come into this one, and we could go to this equation right here. So this is the equation that we're going to use to find that force. The F double prime. Let's take it at A, right? So one of the things we need to get is the moment. So the moment is going to be equal to that force, 150, times the distance. And so that's going to be 12. Let's see, I'll write it here. 12 plus, you can see there's 1/2 of an inch right in there. 1/2 of an inch, and then plus 1/2 of this right here. Well, I can't erase that because it was previously drawn. So it's going to be 1, right? So what we end up with is 2025. And so here we go, 2025, and then Rn is going to be, okay, so this is going to be A, that's going to be Ra, and it's pretty obvious from this very simple problem that Ra, from the center of the bolt pattern to, well, it's actually, I drew it to B, this is going to be right here, so this is going to be Ra, right in there, is just going to be 1. And I should have stuck with green if I was going to, I said I was going to be color coded, but then I lied. So 1. And now we take Ra squared plus Rb squared, but that's all we have. We don't have is Rc. So we take, that's going to be 1 squared plus 1 squared, right? Because Ra and Rb are both 1 squared. I think in the solution, I make it like overly simplified, and I just say, well, you know that it's going to be 1/2 of the load onto the thing. But this ends up being 1,013 pounds, right? But this was the reason why that we had that. So now taking a look at the 2 bolts here, we could say that the total force on A, we notice right here, sorry, I wrote wrong one, is going to be 2,025 minus our 1,013. Well, it should be 1,013 here too. Pounds. And then, but then FB, we see that they agree with each other, and I could put them as minus, but it's really obvious that we're adding them together, so it doesn't matter. And Why did I do that? That's a little weird. Okay, yeah, no, okay. My solution is written wrong there. Why, oh, why, oh, why? I have it backwards, but okay. So that ends up being, oh, wait. I'm sorry. I was looking at this wrong. 75 and 1000 right here, right? So F, and I do have it written wrong. So I think what I've done is I've mixed up A and B, is which one I decided was A and which one I decided was B. So anyway, FA is going to be 1013 minus 75, which ends up being 938. But B, as I've written it up there, is 1013 plus 75. So we end up with 1,088 pounds. And now, so if we want the, then we want to get the bolt area, which is going to be the shear area. So this is going to be the worst bolt, and it's going to be faced with 1,088 pounds. It's going to have pi over 4 d squared, and that ends up being 0.04909 inches squared, and so we end up with a tau of FB, tau of B over AS, or 1088 divided by 0.04909, and that's going to be equal to 22.15 KSI. And then we had the shear. I should have written this over to the side. Maybe I could have done it right away, but the shear of the bolt right here is going to be 0.577 times 36, or let's see, where did I write it? 20.77 KSI. So my safety factor is going to be, let's see, why did I write this right here? Okay, yeah. Safety factor of the thing is going to be N SSY divided by tau, or 20.77 divided by 22.15, or 0.938. And I don't like that. I should have said 0.94. I don't like to go 3 decimal places, but apparently I did that previously. This guy right here, this was not asked as part of this, but what I also did was, what would be the safety factor? I mean, we could do a bunch of different other things. What did I do? Oh yeah, okay, so I looked up in the book and I found out what this was right here. This was 54 KSI was the yield of the member, and then I figured out what the safety factor due to bending was going to be. Right, so because we could ask for a bunch of different failure modes in this. Right. For instance, let's see. I'll keep all this stuff, even though I got to erase it later because I have automatic save turned on, so it's going to save this stupid stuff. This is like a really good. I'm not sharing this. All right. So what we could have done, we could have asked, and it wasn't asked, but we have a bar. Let's see, we have, remember from the drawing right here, we have a bar, and we have in this force right here. Well, it also, the bar could also bend, and because it's so narrow right here, that it's a net. There's a chance that it could bend, and it's weakest right here at that first bolt compared to the moment that's going to be placed on there. So we could like figure out right there at the edge of the thing what the moment is going to be. Right, there's going to be like a moment that's placed right there. So that's a different moment than the other moment that we were looking for. And so that one is going to be this force 150 times 12 plus 1/2, right? So M that we're looking for here is going to be 150 times 12 plus 1/2, and that turns out to be 1,875 inch-pounds. And the moment of we want to find the stress in that section right there. So if we take a look at the cross section of this, about that axis right here, we'd find that I is going to be equal to this thickness times the and this width right here, and then this also has this is also the diameter that's right in there. So we want to find the I about that. It's BH cubed over 12, so that the base is T times W cubed over 12 minus T times D cubed over 12, right? So that the minus is because it's missing this part where the bolt is going to be. So if we do that, we have like 0.25 the thickness. The width of the thing is cubed over 12 minus, now we got the thickness, but we also have the diameter cubed over 12. And what we end up with is 0.02051 inches fourthed. So if we're going to find the stress, we get MC over I, 1,875. Up the C is going to be 1/2 of the section, right? So that's going to be 1/2 of 1, and divided by 0.02051. And what we're left with is a stress of 45.71 KSI. And we had looked up the strength of this material so we can get the safety factor. And that's just going to be, I think, 54 over our 45.71 KSI. Whoop, dummy. It's going to be equal to 1.18. Now there's several other failure modes that I haven't calculated yet. One, it could be bearing. I could also ask for the bearing on the bolt and the bearing on the member, right? So that stress is, so the bearing stress, they're going to be equal and opposite to each other. And the idea there is the in a bolt right here, we are placing in, and maybe I'm going to draw the one that's in A. Right here, there's the bolt, right? And I've exaggerated the size of the bolt and the size of the hole. And one is going to be pressing onto the other. and they're going to it isn't going to go the entire width, but we make an assumption, we make an approximation that instead of what we know would be or can envision happening due to the just like contact stress, where the part that becomes in contact between a cylinder and another cylinder, or a cylinder and a flat plate, or what have you, there's a flattened area. Well, this kind of has the same thing, but there isn't as much of a gap as I'm shown in between, let's say, a pin and the hole, or a rivet in the hole. The bolt usually has a little bit more clearance than those, but we make an approximation and we just use the width of the whole thing. And so what we say is it's going to be the force on the particular bolt divided by the diameter times the thickness, right? So, because that's going to be like the projected area, if you will, if we were to draw the thickness of the plate as part of this right here in 3D. This is the area that we're talking about. So if we had that, what is it? What did I say that this was 1088, and that's going to happen at B. And we have 0.25 diameter, 0.25 thickness, and what we end up with is 1088.25 squared divided. So I end up with 17.41 KSI. And that's going to be compression, and it's going to be experienced by both the bolt and the member. So what we could have is two different safety factors for bearing. We could have it for bolt, and we could have it for the member. And so this is going to be the SY of the bolt divided by that bearing stress. And then we have SY of the member, let's say, divided by that bearing stress. And so this was 36 divided by 17.41, and this was 54 divided by 17.41. So we also here we get 2.07 as a safety factor for bearing stress, and in the other one we get 3.10 as a safety factor. And now there's one more possible, well, there might be some others, but there's one more possible that that jumps out to my mind, is that now what we could possibly have happen, I'll put it onto here, is that this thing could rip out, right? This section, it could shear right along here, where here's the shear area that would happen. It's coming right to there. And so if we were to include that one, pausing while it's thinking. Oh, did I already have a blank one up here? No, I didn't. Okay. All right, so once again, here is the one that I'm looking at. The failure mode I'm looking at is a scenario in which this force is causing a moment, right? That's actually right here, so that bolt rips out here and that bolt rips out here. But since we already have the load on, we know the load of this bolt right here. We're going to use that one and just isolate right here. And so that's going to be the shear. That's going to be a shearing, right? And we can go this could be the rip out. It's going to be the force, not this force, but let's say the force of B, divided by the area of this, let's call it a rip out area to coincide. In that rip out area there's going to be two different areas. There's going to be two of them. So both of them resist this tear out, and that might be another name for the tear out right there. And so it's going to be the thickness of the thing, and it's going to be this dimension x. And if you read the example that's near this in the book carefully, it isn't the distance. It wouldn't be 1 inch, which would be half, would be the location of the bolt with respect to the edge right there where it could tear out. It would actually be, zooming in right here, it would be this distance right here. This is the one that they call x. So it isn't to the center, which is 1 inch. It would be 1 minus the radius of the bolt, and the radius is 0.125. So it's going to be like 0.5 minus 0.125, and I believe that's 0.375. So that's right here. So I would say that it would be 2tx, and so now we have 1,000. What was the value? 88? 1,088? Yeah, 1,088. Divided by 2, divided by 0.25, and divided by 0.375. Right here. And so that's 1088. 2.25 divided 0.375 divided, and I get 5.803 KSI. Now this is shear, right? This is a shearing stress. So if we want to get a safety factor for the rip out, we would take the shear yield of the member, right, and divide it. Well, that shear yield of the member is going to be 0.577 times our 54. Or 31.16 KSI. So it'd be 31.16 divided by 5.803. So not too bad. It's like at a 5.37 safety factor. So not as likely as these other ones. But definitely the first one that's going to shear is this one. That's going to be the shear of the bolt. Is the most likely failure mode. Looks like followed by bending is a hazard, and then bearing on the bolt and the bearing on the member. And remember, this bearing stress, you can think of this as putting a dent, right? Kind of, just if you could picture that, right? You get beyond the yield capacity and compression, and what's going to happen? It's not going to bounce back from where it was, so it's going to leave a mark, right? So this would be leaving a mark on the bolt first, and then it would be leaving a mark. And I often think about that for the mark on the member. It's going to make the hole bigger. It's going to make the hole slightly bigger. Something that you should know about the assumptions that are going on here is that we're assuming that friction does not play a role in this whole situation. But you just know if you clamp this thing down tight enough that friction could potentially hold something in place. So that's part of the assumption. But on the other hand, if you were to use bolts in nuts and bolts in this capacity, this would be a bad design, because any amount of vibration right there is going to loosen some of that friction, right? So you have preload. A lot of times you'll put washers, lock washers in there to try to prevent that from happening. But friction can be overcome by vibration. And that's a natural part of any machinery. If this was in a machinery plant and there's engines and motors and gears and all kinds of things running, there's going to be vibration that's like moving through the structures. And then we also, if you had this arrangement right here, you would want to maintain this thing to be perpendicular. But any amount of the necessary to assemble clearance that you have between the bolt and the hole is going to cause this thing to lean downwards. It's almost inevitable that it would happen. So if you were going to actually install this kind of piece, you'd want to make, first off, you'd probably want to put pins in it, right? So, and you wanted those pins, you would design those to take up the entire amount of the shear load that we are talking about right here. The bolts would just hold the thing in place and hold them clamped together. It would be the pins instead. And the pins, you would make them a pretty good tolerance to avoid this thing happening. But still you might have a little bit of problem, because if this thing's long enough, and even with some tolerance, you're still going to have like a droop. It ain't going to be perpendicular. So if I was designing this, what I would do is I would also put in maybe some type of bar right here that got welded into place so that this thing had to rest onto that. And maybe I'd even put 2 of them in there, so that you would, when you would bolt this thing, because apparently you're bolting it, otherwise you'd weld the thing in there. But if you needed to bolt it, it must be because you need to remove it for maintenance or for whatever you have to do. So let's see, what's my time right here? I got to go eat lunch. So hopefully this was sort of a helpful thing to work through. I guess I'll keep it for now. Is there any questions? Anybody still there? You're welcome. No problem. Hope you guys are having a decent semester, even though this is a crazy time. It's a lot of different challenges to try to be a college student right now. But overcoming challenges makes you a better person. Let's just let's think of it in those terms. So take care, guys. Hopefully, this semester is going to be over soon, and summer begins, and hopefully there's going to be some amount of fun that doesn't involve staying in pajamas all day long in your summer. And so with that, I think I'm going to end the video